hello. Continuing our study this week of maps and flows, we look at some simple dynamical systems. To recap what we did in the last lectures, given a map and an initial point, we are interested in examining fixed points, their stability. We'd like to know what are the periodic points and find out what their stabilities are. And if the system is hyperbolic, namely if the derivative of the map is less than 1 in magnitude at a fixed point or at a periodic point, then the dynamics falls into clear categories of either being attractors or repellers. Let's look at a particular map to get some of these ideas more concrete. The simplest map that one can look at is where the function f of x, let us look at one of the simplest maps, which is known as the Bernoulli map or the bit shift map. The reasons for this name would become obvious. Given a number x multiplied by 2 and do the mod operation. So, this is a map actually on the interval 0 to 1, or you can think of it as a map on the circle, identifying the points 0 and 1. And this map plays a very important role in getting ideas on of nonlinear dynamics in place. Okay. So, f goes to f of x, f takes x from x to 2x mod 1, and many results in this area can be proved for this map using very elementary reasoning. Okay. When you graph the map, it looks something like this. From 0 to a half, it doubles over here, and then once you cross half, it starts again. So, this map is a discontinuous map with the discontinuity at the point x is equal to 1/2, because 0 and 1 can be identified. There's another way of looking at this map is to see its action on a point x. And a point x I can write, now I'd like to write it in not in decimal but in binary, and I write it as A0, A1, A2, A3, etc., which in the usual expansion is A1 by 2 plus A2 by 2 squared plus A3 by 2 cubed, and so on and so forth. Or I can rewrite this as the sum from j going from 1 to infinity aj by 2 to the power j. And any number that lies between 0 and 1 can be written as so, with the aj's, because we are using binary representation, the aj's can be either 0 or 1. So, any sequence of the two digits 0 and 1 have a correspondence, unique correspondence between this sequence of two digits and any point on the interval. The action of the map x goes to f of x, where f of x is 2x mod 1, is to take the point x, which was, as we have just seen, a1 divided by 2 plus a2 divided by 2 squared, etc., multiplied by 2, and remove any part which is bigger than 1. So, clearly what happens is that if I multiply x by 2, I remove that, I remove a power over here, the 3 becomes 2 and this becomes k minus 1 and so on, as I have written over here. And if a1 is 0, we do not have to consider it, and if a1 is bigger than 1, if a1 is 1, then the number is bigger than 1, and in the modulo 1 operation this will get dropped. So, the point x will go to this point, which is a2 by 2, a3 by 2 squared, etc., etc. Equivalently, we can say that x, which started out as a1, a2, a3 all the way through to infinity, will now get transformed to a2, a3, a4, etc., just removing the first digit. I could have taken this binary point over here and just shifted it here and removed the first symbol, and that would have done the same effect. So, the effect of the mapping is to shift this infinite sequence of A's one place to the left. Should that be to the right? Sorry. I shift this infinite sequence of A's one place to the left, and I drop the digit preceding this binary point, and in this first example it was A1. Likewise, what I have just discussed is this first transformation. At the next instant, I take this entire sequence, shift it one place to the left and drop A2. Again over here, I shift it and drop A3, and so on and so forth. This is why this particular map is called the bit shift operator, because the symbols A1, A2, A3, etc. are either 0 or 1. They can only take two values. And the effect of the map is to basically shift by one place, either to the left, and to drop the leading symbol. There are two fixed points of this map. And what are the fixed points? They are either 0 or 1, because 2 times 0 is 0 and 2 times 1 is 2, which is 1, which is also which is a fixed point. And you can see that very simply, because if I have this symbolic sequence, or if I have this sequence binary representation 0, 0, 0, each time I shift one point, if I just keep shifting by one point, I will just get the same thing repeated. So, it is a fixed point. And similarly, for 1, if I just keep shifting, I do not change the sequence at all. The derivative of this map everywhere is 2, as you can see. This is just, the derivative is just 2. And so, since this is bigger than 1 in modulus, these fixed points are both unstable. Starting at a point close by, I can see that I just move outwards. If I am starting over here, I just move down and outwards. So, both these are unstable fixed points. To find points of period 2, we look at the graph of the map f of x. And f of x is the map I have shown over here in purple. 0 to 0.25, 0 to a quarter gets mapped into 0 to 1, quarter to a half again gets mapped 0 to 1, and so on and so forth. Okay, so, you can see that this map is the twice composed map. You have the fixed points at 0 and at 1, and now you have two new fixed points which are created over here. These are prime period 2 points, and it is very easy to figure out that they must be the points 1/3, because 1/3 doubled becomes 2/3, and 2/3 double becomes 4/3, which modulo 1 becomes 1/3. So, these two are just the two fixed points of period 2. Note that if the initial point has a periodic sequence of zeros and ones, then under the map f, the sequence will necessarily repeat under iteration. So, you take this first example here, which is the binary representation of the point 1/3. It is 0.01010101, etc., all the way to infinity. When I apply the map to it, it goes to the point 2/3, which is the same as having shifted this point over here and removed the initial 0. So, that gives me the point 101010 all the way up to infinity. Applying the map again, I now shift from here shift it to the next point, remove the leading 1, and I get again 0, 1, 0, 1, etc., all the way to infinity, and this process will repeat. This is exactly equivalent to writing in in decimal notation. 1 by 3 goes to 2 by 3 goes to 1 by 3 goes to 2 by 3, and so on. Okay. So, every periodic sequence of zeros and ones, or any eventually periodic sequence of zeros and ones, will correspond to a periodic or an eventually periodic orbit in this map. So, here for example, I have started out with some sequence which just terminates in the following sequence 1 1 0 1 1 1 1 sorry 1 1 0 1 1 0 1 1 0 1 1 0, etc., etc. So, this is going to eventually be a periodic orbit, even though initially it was not. Okay. So, initially it was something, and then eventually it becomes periodic. Here I have started with another sequence which is 0 0 0 1 1 1, 0 0 0 1 1 1, 0 0 0 1 1 1, and so on all the way to infinity, and this is another periodic orbit. Any rational number like 7 by 9 in this example over here, 7 by 9 will go to 5 by 9, which will go to 10 by 9, modulo 1 is 1 by 9, and so on and so forth, and it will eventually start repeating. So, any rational, any point x which is rational will either be a periodic part of a periodic orbit, or it will be something which will eventually become periodic. It is also easy to show that there must be prime periodic orbits of period k by simply constructing one. You start by taking an aperiodic sequence of zeros and ones which has got length k, and then simply repeat it ad infinitum. So, for example, to get a period 7 point, I just have to start with 3 zeros, 4 ones. This is itself aperiodic, and then just simply repeat it. If I do that, now this is an orbit which has prime period 7. More than that, there can also be aperiodic orbits, strictly aperiodic orbits, which correspond to aperiodic sequences. For example, if I start with the following number, which is 0.01 0 0 0 1 1 0 1 1, and what you can see over here is that I have taken concatenations of all subsequences of length 1, of length 2, of length 3, and so on and so forth. If I now just keep on extending this, this sequence will have no periodicity. And therefore, if I start with some x naught, which is this particular point, this point will also not be periodic. So, for this rather simple map, this dyadic map or the Bernoulli map, one can show that one must have periodic orbits, eventually periodic orbits, aperiodic orbits, and so on. This has been sort of very nicely systematized through what is known as symbolic dynamics. And there is, as we have seen over here, the binary representation of any point in the interval 0 to 1 uses just these two symbols 0 and 1, and the action of the map is merely to shift this binary point from one location to a single iteration is to move it one place to the right, or to move the sequence one place to the left. This can be systematized in what is known as symbolic dynamics, and in order to do that, let us consider this space sigma 2 of all infinite sequences of 0 and 1. This is also known as the symbol space of 0 and 1. So, sigma 2 is the set of infinite sequences S0, S1, S2, etc., where the SIs are 0 or 1. Along with this space, sigma 2, let us consider the shift map. The shift map takes a sequence, an element or a point of sigma 2, and forgets the leading symbol. So, if I apply the shift map onto the sequence S0, S1, S2, S3, etc., that just drops S0 and gives me S1, S2, S3, etc. Okay. So, this is the very simple action of the shift map on the symbol sequence. Now, the shift map has the following properties. The set of periodic points of the shift map is dense in sigma 2. There are 2 to the n points which have got period n. The set of not periodic but eventually periodic points of the shift map is dense in sigma 2, and the set of points that are neither periodic nor eventually periodic, that itself is dense in sigma 2. A lot of what happens in sigma 2 is mirrored in what happens in our Bernoulli map, but importantly over here we can introduce the idea of a metric on sigma 2 by defining the distance between 2 points. This is easier on sigma 2 than to do it on the interval in some ways. So, let us just consider how do we characterize the distance between a point S and a point T, which are 2 elements of sigma 2. So, S is the element S0, S1, S2, S3, etc., some sequence of symbols, and T is the sequence T0, T1, T2, T3, etc. And the distance between them, which we will denote by d of S and T, is given by this following expression. This is the sum from 0 to infinity of Si minus Ti divided by 2 to the power I, modulus of Si minus Ti. So, this is a Hamming distance, and since the maximum value that Si minus Ti can take is 1, this has to be less than the sum of 1 over 2 to the I summed over infinity, and that geometric series has the value 2. And the least value that Si and Ti can have, Si minus Ti can have is 0. That is, if the point S and T are identical, then then it would take the value 0. So, and you can easily show, and you will show in the homeworks and the tutorials, that d is a distance. Okay, it satisfies the triangle inequality, and it has all the properties of a distance. What is useful about this idea of a distance is to note that since the distance is defined in this way, supposing S and T are identical for n places. So, if the first n symbols of S and of T are identical, then this value over here, Si minus Ti, will be 0. So, this sum that I have, which tells me what this distance is, can be split into 2. One part which is definitely 0, that is the terms from I equals 0 all the way up till n, and the terms which are not equal, which are not or possibly not equal to 0, and that is this particular term over here, which is the sum from n plus 1 to infinity. Now, I can rewrite this taking out 2 to the power n minus 1 out of this in this following way, and this shows that this entire distance must be less than 1 over 2 to the n. So, if things are matching for n places in the symbolic sequence, then the distance between these two symbols is less than 1 over 2 to the n. This gives you an idea about distances in this space sigma 2. To make this more concrete, if the first 5 digits of S and T are identical and the remaining are possibly different, so say S and T are S is 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, etc. something, and this is S and T I write as 0, 1, 1, 0, 1. Oops. And then it could be 0, 1, 1, 1, 1, 1, etc. It could be any old thing. So, they are matching in the first 5 places, they are identical. In the first 5 places, they are identical. Then the distance between them has to be less than 2 to the minus 5 or 1 by 32. Now, if I operate by sigma, I have to drop the first digit. And so, these two new sequences are only matching for 4 places. And so, the distance is only less than 1 over 2 to the 4. If I apply sigma again, then if I apply sigma again, I drop one more place, and now these two symbol sequences are only matching for 3 places. If that is so, then the distance between them is only 2 to the minus 3. And if I apply the shift operator 5 times, I wipe out the first 5 digits of both of them, the first 5 symbols of both of them, and now the two sequences don't have anything necessarily in common, and so the distance has got to be only of the order of 2 to the 0, which is 1. So, under the shift map, the distance between 2 points doubles at each iteration, and this is a very important idea in this field, and it is known as sensitive dependence on initial conditions. Formally, if D is a metric space with metric D, and that is what we have done over here with sigma 2 and the metric defined by small d, the mapping sigma, which is in this particular case a shift, shows sensitive dependence on initial condition if there is some delta positive such that for all x in D and all epsilon greater than 0, there is some y and a number n such that the distance between x and y initially starts out by being less than epsilon, and the distance between the nth composed, the map applied n times to x and the map applied n times to y, that becomes bigger than delta. In other words, no matter how close 2 points are, there will be some number of steps later when the distance between them can be as large as the system might allow. Nearby points will not always stay nearby. How long will one have to wait to see this separation of these two initial points? This number n will depend on epsilon, it will depend on delta, and it will depend on this function f. Namely, how close do the initial points be and how far away do they get? That depends on the map f. But this idea of sensitivity to initial condition is extremely important in this field, and it is the hallmark of the kind of motion that is commonly termed chaos or chaotic dynamics. Now, we have introduced this in the context of symbolic dynamics that corresponds to a very simple mapping. The manner in which more complicated systems show such behavior is actually very similar. Namely, at each step, the distance between two nearby points increases by a factor which is larger than 1. And here in this example it was 2, but it just has to be bigger than 1, and so two nearby points will eventually become further and further apart. So, the concepts developed here have wider applications. In the next lecture, we will take up some of these other applications in similar but slightly different mappings.